Alright, welcome back to week 12 problem solving session. I am Shreya, the TA for the course, and today I'll be showing a few. First of all, I'll be discussing week 12 assignments and how to solve them using R, and then I'm going to show you how we can use R to perform some regression analysis and time series analysis, and how to get solutions to questions that we had previously done using the software. So before proceeding, I'm going to stop the screen right now and let me know if you can see the entire screen, okay? Can you see now? This Google?
Yes.
Okay.
Yes, sir. Google.
Okay. So first of all, as I said, I'm going to start the discussion. Yes, it's recording. Yeah, so I'm going to start the discussion by solving week 12 assignments, and then I'm going to move on. Okay, so let me go to week 12 assignment. So I hope you all have solved these. So how should you proceed? So now we have this Excel sheet where we have data on year, savings and income. So first thing is to get the data and download and get it downloaded and saved in a place. So I have already done it and copied the dataset in an Excel sheet, and then I have saved it as a q1.txt. So I saved it as a tab delimited text.txt function. Okay, fine. So once I save it, I'm going to open the R console, create a new script, and if you remember, in order to call data sets, we at first have to set the working directory. So here, this is the problem thing. So I'm going to go get the info column, and here I'm going to get the file path. You can also do the same. So first and foremost, we have to set our working directory. So then we are going to use this command set wd. Within quotes, we are going to specify the path to our working directory. Okay, so I would request you to do this along with me so that we are on the same page. Okay, so once we have set the directory, another important thing is to save our scripts. So I'm going to save my script as, let's say, question1.r. I'll save it here. Solved. Okay, so it's important to save our documents to keep a log of the codes that we are using. So once this is done, this is my console. This area is the plot area and help packages, installing packages area. The plots will appear here, and this is my global environment where the R will show which variables or data sets are loaded in memory. Okay, so once I have set the data frame, I am going to import my data set into a data frame. So as I was saying the last day, let us write this data set is, one second. Okay, so this data set, as I was saying, it has information on year, savings and income. So let me rename. I want my data set as saving income data. Okay, this is just a nomenclature. I want to save my data in a data frame which is named like savings incomes data. So this one I'm going to put an equal to. In this data frame in variable, I'm going to assign, I'm going to read the value of this file. So this is a tab delimited.txt file. So as I was saying, the best way to do is to read it as a table. Read.table or read.csv. I'm going to use a table. Then I'm going to specify the name of the file. So this one was q1 or q1.salt. I have to see. 1 second. Yeah. So this is q1 salt.r and the text file is q1. So okay, I'm going to call it from here q1 with the extension, and to be on the safer side, header equals to true. Okay, and then I'm going to see the first 5, let's say, rows of this data frame. So I'm going to write the name of this data frame and I'm going to put n equal to 5. Now if I run this, for running I have to press Ctrl and enter. So this as you can see, whichever line I am running, that will appear in the console. So I just ran the setwd command and it appeared in the console. Okay, so now I'm going to run line 2. So right when I run it, it comes like this: savings incomes data. This is run and the data frame is loaded in my memory. So I can use this to see if it has been loaded correctly. So yeah, it has been loaded correctly. I have 12 entries on savings and income. Also, if I want to check directly from the console how the first 5 rows, I'm going to use this. So this is giving me the first 5 rows. By default, if I don't put this n equal to 5, it will show me 6 rows. But since I want 5, I could even want more. I could want 7 or let's say 9. So as many number of rows as I want to see, I can specify over here. For the timing, let's keep it at 5. Okay, so this data set is now loaded in my system. Now let us go and check out what were the assignment questions. So first we have loaded this up. So this data set gives data on personal disposable income, which is my X. So income is X or the regressor or predictor, and the response is the gross domestic savings. So savings is my Y in crores of rupees from this period to this period. So what is the estimated Keynesian savings function for India during time period 1974 to 1995 to 1996? So basically we have to find out this savings function. Savings is a function of income. So we have to regress savings on income. How will we do that? So in order to do a linear regression, we use the command lm. We'll use the headers of this file. So we are going to regress savings on income, and the data set is savings income data. Okay, we want an intercept term, that is why we are not putting a -1 over here. If it would have been said that fit a regression without the intercept term, we would have put -1 over here. This would give us a linear regression without intercept. I'm going to run and show you again. So let me run this line. Okay, so here I'm getting the intercept as this minus 10.10991.347, and the slope coefficient is 0.297. Okay, so this is the correct regression. So the answer is this one. So if I just so this one, 10.991 and 0.297. So the closest one is this one, minus 10.990 plus 0.3x. So this will be the answer. Is it okay? Alright. So once we have it, the question was, what is the value of the t statistic for the slope coefficient? Is it significant? Now, how will we get the value of the t statistic? So let me do one thing. Let me first save this regression model, and I'll save the output in model. Let me write it as model question 1 equals to this thing. I'm going to assign this, save the regression values and everything pertaining to this in module.q, module_q1. So I'm running it now. See, this is actually a list of 12 data structures. So we have the coefficients over here, the residuals over here, the effects, that is the betas, fitted values, that is y hat predicted, then the df dot residuals, x levels, and so on and so forth. So many terms here we have. Okay, so now once I have saved this regression in this data structure or list, I need to find out the t statistic for my slope coefficients. So for that I will use the command summary model q1. If I enter, then this is my output. Okay, so what is the output will display what formula I have used, what is my response, what is my predictor, what data set I have used, the 5-point summary of the income column, and then this is my regression result. Okay, the t value is the student's t that we were discussing last day, and this is the associated p value. Now for both the intercept and income, we see that the p values are highly significant. Okay, so now what did they ask? They asked for the value of t statistic for the slope coefficient. Is it statistically significant? So yes, it is statistically significant. It would be either A or D. So now we have to go and check the t value. T value is 49.402. So then the answer is A, 49.4, and it is statistically significant. Is it okay? Alright, so from this summary, what other things do we get? We get the residual standard error, what it is, and the degrees of freedom associated with my RSS, residual sum of squares. Also, we get the multiple R square, that is the coefficient of determination, capital R square, the adjusted R square, and the F statistic with the corresponding degrees of freedom. Okay, and the p value. So from here, what is the value of the F statistic is the model overall. Yes, you want to say something?
and R square both are same thing.
Sorry, can you be a little louder?
Yes, ma'am. I'm saying that the multiple and R square are both are same thing.
Yes, multiple R square and coefficient of determination are the same thing. This one. But multiple R square and adjusted R square are not the same thing. Okay, so the difference between multiple R squared and adjusted R square is like so if this is my multiple R square, let's say so this will be sum of squares due to regression, let me say, divided by sum of squares total. So you remember there was this identity, if we go that total sum of squares can be split into, like total sum of squares can be split into sum of squares due to regression plus sum of squares due to residuals. Okay, so if I do sum of squares due to regression by sum of squares total, then I am going to get the R square. But the same thing if I do it with the mean squared error, so that is going to give me adjusted. R square adjusted is basically mean squared error due to regression by the total. Okay, so if you remember the ANOVA table, let's say this is my ANOVA table, this would be, one second, so here I would have my sources of variation. This would be regression, this would be, the next one would be error, and then we would have total, and then we would have degrees of freedom, and then we would have sum of squares, then we would have mean squared equal to sum of squares by degrees of freedom. Okay, so adjusted R square is this one. So always total degrees of freedom was n minus 1. For a simple, this I am writing for a simple linear regression. Which means only one predictor. Okay, so then this one would be n minus 2 and this would be 1. So this will be SS regression itself, but this would change. Okay, so here the adjusted R square and R square, they are changing because this one, the error, the regression remains the same, but MST, this becomes SST by n minus 1, and that is why the adjusted R square initially it is changing. Okay, so here for this thing it is showing a changed result. Do you understand? Is it clear? Okay, so if I want to get the ANOVA table, as I was saying, I am going to write ANOVA model underscore Q1. So this is giving me the ANOVA table. And this is my F value, which is similar to, which is rounded up and here. So it's same thing, just it has been rounded up with the associated p value. So whatever F result I'm going to get from the ANOVA table, the same thing only I'm going to get from this summary. Is it clear? Any doubt? Please ask.
No, ma'am.
Okay. So then this is done. What is the value of the F statistic? Is the model overall statistically significant? The answer is yes. The DF is 120. And see here it is exactly matching with my result. But they are saying it's not statistically overall significant. But that's not true. So the answer will be this one, to round it up. And yes, the model is overall statistically significant. Alright. So then the question is, we have to test for homoscedasticity using Bruce-Pagan test. What is the value of BP statistic? Is the homoscedasticity assumption valid? Okay, so in order to use the Bruce-Pagan test, we have to install or get this library. So I already have it installed, that is why it is coming like this. Okay, it's all. If in case you do not have this installed, you have to use this command install dot packages, and then you have to get lm test. Okay, even though it is installed, I can just install it once again. So now if you can see my console, it is going to this URL and getting the required package. And once a package is installed, you will get this sort of a command that downloaded packages, binary packages are in, and the file path. Okay, so once you've downloaded packages, required packages, it is advisable to put a comment over here. Otherwise, as and when you run the script, the package will get updated, and you don't want that, because while this package is really small, some packages take very long time to load and install. Okay, so once I have this lm test, I can look for here. So here I have lm test installed. So this is the documentation. What sort of test do we have? So Bruce-Pagan test is this BP test. Okay, there are several other functions that we can use from here. The Granger causality test is here, Goldfeld quant test is here. Whatever we discussed, many tests are related to these the concepts that we had discussed in the entire course. They will be present over here, the Durbin-Watson test and so on and so forth. Okay, so you can go through these packages and vignettes and other documentation and find out more. So for the time being, I'm going to, for this heteroscedasticity or homoscedasticity test, we know we have this Bruce-Pagan test. So we are going to go ahead and apply that. So how do we use it? So if I don't know, absolutely I'm not aware of how to use a test, I might go to this help page and let us see what we get over here. So this performs a Bruce-Pagan test against heteroscedasticity. We have to give the formula over here and the van formula, whether you have to mention if we have to do a studentized residuals to get the studentized version of the test statistic. Okay, these are the arguments, whatever and what all they mean, what this test does, what is under H naught, and so on and so forth. So this fits a linear model to the residuals of a linear regression. By default, the same explanatory variables are taken in the main regression model, and rejects if too much of variance is explained by the additional explanatory variables. Okay, so we can check the original papers over here if you are interested, and here in examples you will have small sections of code snippets how to perform Bruce-Pagan test. Okay, so first they are going to this part caters to generation of data. Okay, so replicate will generate this -1 1 50 times. Okay, and then they are going to create disturbance terms, add the error terms for the two regressions, and they are going to apply and see what is going to happen. So here, if I have to apply the Bruce-Pagan test for heteroscedasticity, I have to apply BP test, and I'll give this is my formula, LM whatever I've used. So I'm going to give this one here, and I'm going to run it. So here they are saying could not find BP test. But why is it they couldn't find BP test? Because I have installed the package, but I have not loaded in memory. I've written it down, but this has not yet been run. It is not appearing anywhere here. So after installation of packages, you make it a point to use this library command to load that package into memory. So first I'm going to do this. Then I'm going to get something like this, loading required packages. These are the required packages, and then we are good to install and run this command. Now suppose you are running some library, some package name, and you find that this required package is not there. Then it is advisable to install the packages that are prompted by R manually, and then again proceed. Okay, so here I'm going to do again library LM test, then I'm going to do a BP test. So this is giving me the studentized Bruce-Pagan test. This is my test statistic, and the p value is 0.0005, which is less than 0.05. So in Bruce-Pagan test, the H naught is that there is homoscedasticity. So for Bruce-Pagan, for BP test, the H naught is no heteroscedasticity. Okay, so now here we have the p-value, the associated p-value as 0.0005, which is less than 0.05. So what we are going to do, this is I'll just copy this thing in this file. Okay, this is the output. So this thing is less than my level of significance. So thus what I'm going to do, we would reject null hypothesis and conclude that there is presence of heteroscedasticity. Okay, homoscedasticity assumption is not valid. Okay, test for homoscedasticity. What is the value of the BP statistic? It is 11.821. So either this one or this one. And the answer is no, the homoscedasticity assumption is not valid. Is it okay? Any doubt?
Okay, ma'am.
Okay.
No, ma'am.
Okay. So now let us move on to the next one. So here we have another data set where we have year and real GDP are in rupees in crores mentioned for how many rows? 48, so 47 rows, let's say, for 47 data points. So again, what I'm going to do, I'm going to copy this into an Excel sheet. So I've copied it now. Okay, so I have data till 2006. It's visible, right? I have data till 2006 and there also. So this one I don't need anymore. I'm going to remove it. 2006. Okay. So now they are saying what is the estimated linear regression of real GDP on time variable. Okay. So the same thing I'm going to save it as, let me save it as a CSV file. So I'm saving it as q5.csv. So here also I have to change the file format. Even if I don't specify the extension here, the file format needs to be changed. Okay. So this is now saved. So now I am done with this data set. If I want to remove everything from memory, I can use this brush tool. So that is going to remove all variants from the memory. I'm going to close this one. I'm going to clear the console. In order to clear console, we would press Ctrl L. Okay. Okay, now let me open a new script. Here again, before proceeding to anything else, we would have to set a working directory. So as we were saying for the previous one also, let me see if I open my file. Recent files is this one, let's say. So I just copy this line here. So I've set my working directory here. I'll save my script. Let me save it as Q5. Alright. So once I have set the working directory, this is now set. I'll load question 5. So this is GDP data. So let me write it as GDP data. That's the identifier name. I saved it as a CSV file. So I'll do read.csv question 5.csv and header equal to true. Okay, now I have this one. Alright, so now I need the linear regression equation. So what I'm going to write it as model GDP equal to LM, name of the y variable. So we are regressing this one on year. So I am going to write this name. So here in console, if I want to get the first few rows, just look at the data. This is my column name. So I'm going to regress this thing on year. Okay, so let me run this. See, the error is this object, this is not found. Now this will happen if I don't specify which data it should look into to find these columns. Here I forgot to mention the data set, from which data set they should take. So there we have to write GDP data. Okay, so now if we run it, I have this model GDP list of 12. So if I just view this one, model GDP, I'm going to get the regression line, minus 8877466945,273. So is that the regression line? Yeah, minus 88774669 plus 25273, 45273, this one, option A. Okay, this is my regression line. Now they are saying find the predicted value of the real GDP for year 2007. Now, is 2007 present over here in my data set? That first thing I'm going to check is that. So 2007 is not present. So I have to predict 2007. This is kind of a new data for me. Okay. So in order to predict new data, what we should do, we should make a data frame with exact same column names and supply that to the model or to the predict function that we are going to use, and then get the values. So what I'm going to do is that I'm going to create, let me see, I'll rename this as GDP new, and this would, I am creating a data frame using this data.frame command, where my year will be, let's say, 2007 and 2008. Okay, so this is my data frame with this year, with the information on predicted variable. Now if I have to predict, I'm going to use predict, my formula or model name. Using this model I'm going to predict, so model GDP, and then data I'm going to give as, or I should specify new data equal to GDP underscore new. So if I run it, I'm going to get these values. So this one is for 2007. This is the prediction for 2008. Is it okay? So 2088391 is my answer. That is the predicted value of real GDP using this model for 2007. We had data till 2006, so we are predicting for the next time point using this data. Is it clear?
And same thing we can use in the yes ma'am. My question is that same prediction can be used in population also. If the census is not going on,
yeah, the census
can we
is
use
usually
this
10
prediction
years.
model there also?
Yeah, census is done usually 10 years. We can use, but I highly doubt it will be so simplistic. But yes, of course we can, because every 10 years some census is going to happen. So if we want a value in the middle, like after 5 years, 3 years, we can use this year as that middle thing, and then get the predicted value of our population. Okay.
Okay ma'am, thank you. Okay ma'am.
Thank you. Alright, so now we know how to generate predictions with new data. But suppose if I want to find out if using this same thing only, I want to get the prediction for 2006 data. So then I can just write down this predict, my model GDP, and the 47th observation. So here the 46th observation was 287, something like this according to my model. The 47th observation is this one. Okay, so this is the predicted value, this is the observed value. If we subtract, we are going to get residuals. So if in order to get residuals, we would like, we would use this column resid and give the model name. So here you see I get 47 residuals from this OLS model. An important thing to check even for heteroscedasticity is randomness of residuals. So we can plot this resid model GDP. This will be my Y column. X column would be year. So that will be GDP data dollar year. And Y would be this one. Let's see how the scatter plot looks. So the scatter plot looks like this. There is a definitive pattern. So definitely this is not random. So there could be presence of heteroscedasticity. Okay. So residual plot will show us visually whether there is randomness in the data or not. If there is randomness in the data, that residual versus X graph or residual versus predicted graph. So here if instead of residuals, if instead of X, if we give predicted also, predict model underscore GDP, we'll get the same thing. Okay, but keep this in mind, this predict thing we usually will use when we have more than one predictors in mind. So let's say if we have two or more predictors, so then we will not be able to specify, like we would be able to get for each of the x's how does the E versus X graph look like, but overall we won't be able to deduce anything. So mostly in those cases we use the predicted y hat EI versus y hat graph for this detection of the randomness of the residuals of the model. Okay, but in case of in case of simple linear regression, we can use this predict or the x values interchangeably. Okay, all right, so we have got the plot even though they did not ask. So this thing could be due to some, so you see there till here it looks like there is some sort of correlation between the errors. Okay, there's a definitive pattern. So let's see if that holds or not. So here they are asking to test for autocorrelation using the Durbin-Watson test. What is the value and what do you conclude? So in order to perform the Durbin-Watson test, we would again use that LM test module. So we would load library LM test. So if you remember, LM test had the Durbin-Watson test, DW test, and then you could specify whether we wanted a two-sided test or a one-sided test. We could specify. We would go with the default one. So if we do a DW test over here, 1 second. Okay. So DW test, and then we would give our model name, model GDP. So then the p-value is very small. This is the Durbin-Watson test statistic, and alternate null hypothesis is no autocorrelation. So DW will be close to 2. But here the alternative hypothesis, true autocorrelation is greater than 0, that is positive autocorrelation. And you also see the Durbin-Watson test statistic value is close to 0. So if you remember that line that we showed previously, so if this is the line, this is no autocorrelation. Here I would have positive and here I would have negative. This would be towards, this would be close to 4. This would be 2 and this would be 0. This is my DW. Okay. So here also we observe the same pattern. It's close to 0. So the alternative hypothesis is true autocorrelation is greater than 0. Errors are positively autocorrelated. So same thing we can see in the plot as well. Can you see? If we would have negative autocorrelation, we would have this alternating pattern. But now it's decreasing, so it's decreasing. Then it's increasing, so it's increasing. So this is indicative of a positive autocorrelation, and that's what we tested for. Is it okay?
Okay, ma'am.
All right. So then I've come to that discussion. This is entirely done. All right. So now I'm going to show you something else what we can do with the time series in the time series framework. But before that, let me just show you, if you want to perform those unrestricted versus restricted models that we talked about a lot, how we are going to do it. Okay, so let's say here this is my GDP score on regression or something, and let me just arbitrarily, oh okay, I'll do it in a separate file. So let me just create this arbitrary data set. Let this be my X column. Let this be the Y column. Okay, let this be X1. And let me have something like X2 and X3. Okay, so I'm just going to randomly generate numbers over here. Sorry. Okay. Okay, so let this be my data set. I'll save it as something else. Let's say I'm saving it as one second. Okay, I'll save it as unrestricted restricted example. Dot, let me save it as a CSV. Okay, fine. So now that we have this, I'm going to load it here again. I'll clear everything, clear the console, clear this. Alright, so again I have to set that working directory. Fine. Now I'll save this file as that restricted unrestricted. Okay. Now I'll load the data set. Let me name it as restricted unrestricted data equal to read.csv. What was the name of the data set that we gave? Unrest example.tsv. Okay, I'll load this data. So here we have 47 observations on 4 variables. Now if suppose okay, so I have y on which can be regressed on x1, x2 and x3. Okay, now actually if I have to write equals to some beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. Okay, let's say this is my model. Okay, this is my model. Now let's say my null hypothesis is to test if beta 2 equal to beta 3 equal to 0. So for this what we are going to do? So the steps are number 1, we are going to fit unrestricted model. Then we are going to fit a restricted model. Get sum of squares residuals in both cases. And then the f value is, how was the f value? If you remember, how did we calculate? This was sum of squares error from the restricted model minus sum of squares error from the unrestricted model. The entire thing would be divided by number of restrictions, and this would be sum of squares error from the unrestricted model divided by df error from unrestricted model. You remember this, right? And this would follow an F distribution with error degrees, with number of restrictions and df from SSE DF from unrestricted model as degrees of freedom. Okay, this one you remember, right? So now how we are going to get this from here? So same thing here, we would fit first the unrest model would be LM. What are the header names? Y, x1, x2, x3. So we would fit y on x1 plus x2 plus x3. And we'll see what we get. So here again I forgot to mention the data set. That is why R is clueless. If by any chance, by mistake, there is some y variable in this in my memory already loaded in memory, it is going to take it. Okay, so please be careful as to use the data set here, so that R knows from where it has to extract the y variables. So okay, I have the unrestricted model. This is like this. This is the intercept term beta naught, beta 1, beta 2, beta 3. Okay, if I have to check individually if they are significant or not, we'll same thing, we'll do this command and see that x2 and x3 are not that significant. From here also there is evidence that they are not significant, but together are they not significant? Because these are all singly tested, not tested together. So then what we are going to do, we are going to find out. So here I have the restricted model where we are setting beta 2 and beta 3 to 0. So we are going to set y on x1. That will be my restricted model. Okay, so we'll see how the restricted model looks like. Same thing I forgot again. Please don't be like me and enter your data. So this is the restricted model. Now I have to get the sum of squares. So in order to get the sum of squares errors, I should have the ANOVA tables. So if I give ANOVA of unrest model, this is my sum of squares due to residuals, this figure. Okay, and this is the mean square due to residual from the from this data set. So here let's say I have this figure, so I'm going to save it here. Sum of square error from unrest equal to this thing. Okay, and from, if I do a ANOVA over here, then this is the sum of square error from the restricted model. Okay, so then the F statistic is SSE res minus SSE unrest divided by number of restrictions. How many? We are setting two variables to 0, so it will be divided by 2, whole thing divided by SSE unrest divided by the degrees of freedom of the unrestricted model, that is 43. Or instead of this thing, we can directly give the MSE unrest. Okay, but in order to keep parity, I'm going to give this one only. So this one, sorry, this thing, sorry, here I'm going to write SSE unrest divided by 43. Okay. So what is the f value coming as? F value is 0.1535. Okay. Now I have to get the critical value, right? So how will I get the critical value if I am not supplied? So for that I have to use QF command. Okay, you can see the documentation if you press F1. QF command is going to give those problems. So I want the upper alpha percent. 0.05 is my level of upper alpha level of significance. So I have to specify over here 0.1 second 0.05. df1 will be 2, df2 will be 43, and we have to specify this lower dot tail equal to false. If we do this, then we are going to get that point above which 0.05 area will lie. If we don't give this lower dot tail equal to false, it is going to show that point below which the area is 0.05. Okay, so if we don't use this one, we have to use 0.95, df1 equal to 2 and df2 equal to 43 if we don't use this one. Okay, these can be used interchangeably. By default, it is going to give the area, that point below which the area is what is specified. Okay, so now you see this one and this one is the exact same thing. So this is 3.21. Now our f statistic value is less than the critical f point, and that is why we do not reject the null and conclude that yes, this one and this one, they are actually equal to 0 or are insignificant. Is it clear? Any doubt?
Okay. No, ma'am.
Okay. So you can, whatever f test you have, if you know the logic, you can just get it from here, the values, and then you can go for testing. If you want to, here like I copied the numbers. If you want exact numbers, you can just play around a little bit. So if you do ANOVA model and then you can give a dollar sign or something, there will be ways to extract. So if you look at the structure of this thing, okay, this is not model, this is something else. Okay, so here you see, if you do this one, you are going to get it. So if I want SSE unrestricted from this model, if I want the mean squared thing, then all I need to do is that I have to find out this ANOVA res model dollar. I want the coefficients, right? I want the sum of squares, last one. So this one, if I do sum or this one df, classes and data frame, there are ways to get the values over here. Right now I'm not able to do it, but you will be able to do it something. Okay, so there are ways from which you can directly, instead of copying, you can get it from here if you want to be too accurate. I'll see if I can find out this thing, how you can do it, and I'll show it to you tomorrow then. Okay, alright. So this was all about the restricted unrestricted problem. So far, any other doubt?
No.
Okay, so if there is nothing else, then I'm going to show you how we can go about and do some sort of time series modeling. Okay, so let's say I have a data set like this, okay, which would give me the total number of passengers traveling via airlines from 1949 to 1960 in via a particular route. Okay, this data set is a time series data set. Even though it is represented in this format, we can essentially this is known as a wide format. Okay, technically I'm telling, but we can just make the entire thing into 3 columns, right? Year 1949, January to December, and the corresponding number of passengers. So that format is called the long format. So let's say the data set is given to you in this format. How are you going to analyze? So first things first, I'm going to open and set the directory. Alright, so now I have this. I'm going to save the data set in. So before going that, I'm going to see how this is saved. This is saved as a CSV file, so I'm going to read it as a CSV, airpassengers.csv, header equal to true. Okay, so if I do a head command, I'm going to see how my data set is represented. Now it will be difficult for me to assign time series in this format. So if I can get all the values chronologically arranged in one column, it will be easier to get a plot and get the time series. I mean, assign that time series to my thing. Okay, so what I'm going to do, I'm going to first convert these things into a long format. So for that, I need a package known as dplyr. So I'm going to load it here. Okay, so as I load it, you'll see attaching package these. Then let me put the data frame name as air2. So this thing I'm going to write as air, then I'm going to give this sign and use a command which is known as pivot longer, where I have to specify the columns. So I need this one, I need from this is column 1, so column 2 to column 13 I need in a separate column. So here I have to find calls. I'll give 2 to 13, comma, the name of that column. So what I'm going to do, I'm going to do a transpose of this part of this thing. So I'm going to have, I want a column which will be titled, which will have a header month, and it will have January, February, March, like this. So that name we have to give like this, names2 equal to month, and then values2. So this one I'm going to give air passengers. Let's see. Okay. It's not present in dplyr. Okay, so they are saying this package is not available here, but I think this is available. Let me see. Pivot longer in R. Okay, so this is available in tidyverse package. So I was wrong here. I have to load this package, tidyverse. Okay. So this one is going to convert. So I have all the packages here loaded. So now I have this column. Initially I had this one. Now this was in wide format. Now I have everything in long format. Okay, and this is my time series plot. So now I am going to assign this as time series. So I'll write it as ARTS equal to TS of, because if you remember the lectures, we have to specifically assign columns as time series for R to know that it's a time series data. And frequency we are going to give 12, because these 12 data points correspond to 1 year. Okay, all right. So this is my time series. Now if I want to get a plot, I'll see how I can get a plot. So this is a plot of my time series. So if you remember, there are three major components in a time series. What is the trend component, one is the seasonal component, and one is the this random component. So we see for each of the time points, like this pattern is repeating for like each year. So these patterns are the seasonal patterns, because we have seen that seasonality is the fluctuations which last for at least, usually less than a year. So these seasonal fluctuations, these are the seasonal fluctuations, and there is a long term movement of the curve. So it's not falling flat, it is like increasing with the fluctuations. So this long term gradual increase is the trend line. Is it okay? Now we can make this plot a little fancier by adding labels. So if we add S lab equal to time, and then Y lab equal to air passengers. So this is the plot. Now if we want to get the trend of this curve, there are two methods. We could fit a straight line. We could very well add, like, do an LM. Let's say if we are fitting a straight line, let us do LM data equal to air, let's say Y equal to air, this one, no, air passengers. So this is air data equal to air 2, Y equal to air passengers, and X equal to something. If I write row names of air 2. Okay. passengers. Why is it not coming? Alright, we could also write it like this something. This is air 2 on air passengers. We regress it on, let's say, air $2. We can't do it on year because then it will show different results. If we can add one column, let's say air $2 row something like this, okay, equal to C12 in row air 2. Okay, so then what we are essentially doing is that we are adding one more column here. These are the time points, 1 month gap. So we can regress then air $2 air passengers on air $2 on air $2, this one row number, let's say. So okay, this one we can do an ab line of this thing, or this is the straight line fit that we are getting in the model. Okay, we could also get some other fit also. Alright, so we could also get a quadratic fit if we do something poly, this thing 2, okay, and then we give blue, let's say. There is a function named poly, you can just check out how to do it. Okay, so we would be able to fit a trend line in this manner as well. Now if we want to go for a moving average thing, because moving average is also target getting the underlying trend. So to get the moving average, we would need a package which is known as TTR. Okay, so once we have this TTR, we have to, so let's say I give air moving average. Let me take moving average is over 12 months. Okay, moving average 12. So for calculating that, I have to use this SMA. I'll give the name of the time series AIRTS, and I'm going to specify the number of periods that moving average, number of point moving average I'm going to take. So if 12 is like too strict, I can say take a 3-point moving average. So I'll do a 3-point moving average. Okay, so now if I plot this thing, I'm going to get these. If I do a 12-point moving average, then I'm going to get the trend line. Okay, so if I want to see both the things in one place, I'm going to write this partition mf row equal to C12. So I am partitioning it into one row and 2 columns, let's say. So I'll draw this one, and then here I'm going to draw this. So you see, this trend can be captured by the moving average values, 12-point moving average values. So we can take these values and then we can remove it from the original variable. Then we would get a trend adjusted model. So let's suppose I do this AIR TS minus AIR MV3, and if I do a plot, then most probably I'm going to see, okay, I'm seeing fluctuations here. So it's not exactly adjusted. There are still some other seasonal fluctuations that are involved. Okay. Essentially, if I could have removed the trend component entirely, I would have only gotten the seasonal fluctuations with no change in their magnitude. Only the pattern would have repeated. Okay, something like this. So I hope I'm making myself clear here. So what I'm essentially doing is that I'm doing a decomposition of time series. So now if I have to formally decompose a time series, what should I use? Decomposition can be in two forms. One can be the additive model and one can be the multiplicative model. So if you remember, we had here, like, this is a time series, let's say y, then we would have this, if we keep it trend plus seasonal plus cyclical plus random. So this would be my additive model, and this one, if I do, if my model is like this, then I would get a multiplicative model. Okay, so if I have to decompose a time series, how should I do it? So for this one also we need this library, TTR. Alright, since we already have it loaded in memory, I don't need to reload, but still I'm going to write it so that we remember to use this library if we have to do some decomposition. So let me store this thing as ARTS decompose additive. The command is decompose and nothing else. So if I see, this is a list which will give me the seasonal, trend, random and all components. Okay, so if I do a plot of these things, this is the decomposition. This is my observed series. This is a trend line obtained by moving average. These are the seasonal components. You see, same repeating patterns, and this is my random component. So if we want a trend, and here it has been assumed that the cyclical component is 0, because it usually arises if we have data over 5-10 years, like a long period. Okay, all right. So now if we just remove the trend and seasonal components from these observed values, we would land up at the random point. Okay, so I'll show you here. So if we want an adjusted, let's say, trend, seasonality adjusted, so this is an additive model. We have estimated these components. Okay, cyclical is 0, so we'll just strike it through. Okay. All right. So cyclical is 0. So if we just remove, we have the estimates now of this one, trend estimate and seasonal estimates we have. So if we remove it from the observed value, we are going to get a trend and seasonality adjusted model. So if I want to get this thing, I will write air TS minus air TS decom A dollar, the trend component, minus, or if I add a plus over here, I'm going to add a bracket over here, air TS decom A dollar seasonal. Okay. So if I do a head thing of this TS adjusted, so they are doing essentially a 6-point moving average. Okay. Now this one and the random component is exactly the same. So if I can show you here, this air decom dot random, if I get the first 9 rows, you'll see they are similar. So essentially what we are trying to do manually, the software is doing it by itself, and then it is giving us the random component. Okay, so this is for the additive model. If we want a multiplicative model, how will we fit a multiplicative model? This was all about additive modeling. Now if we have to fit a multiplicative model, again we have to load the same thing. We have to use this library, and here we have to give type equal to multiplicative, and then we'll see how it differs. So this is the plot of multiplicative time series. Okay. Now in case of multiplicative time series, how is the time and seasonality adjusted thing we'll get? So we have to write down TS adjusted multiplicative equal to the entire thing. Instead of plus, it will be replaced by multiplicative sign, and wherever it is minus, we'll have division. Okay. So if we just look at this thing, head of TS adjusted multiplicative and head of this thing, then we'll see it's the same. TS adjusted, oh okay, here it should be changed. These are multiplicatives now. See, it's the same thing. So this is how we can decompose these models, and then we can go for modeling this random part, or if it is entirely random, we don't have to do anything else. If we want only seasonally adjusted models, let's say there is no time component, we have something like this only, fluctuations, and there is no long-term increase. So if you want to get those kind of models, so if you have to get seasonal adjusted only, what we have to do is that we have to take the original one, and if we have an additive model, then remove air TS decom A dollar seasonal. So then if we do a plot of this seasonal adjusted, so you see the seasonality component is being taken care of, and this becomes whatever fluctuations it had, it has reduced and it has become a more flatter version. Is it okay? Now this one, this had a trend component, seasonal component, could have had and a random component. So the series as a whole is kind of non-stationary. Okay, so if we want to test, if we have such non-stationary time series, I'll plot it again once more. We can get the ACF and PACF curves. So you see the autocorrelation function at lag 0 it's always 1, and it is always crossing this threshold, which shows that this is graphically, it is showing that this series is non-stationary. Okay, and PSCF also, if we do, then we see that okay, could be something. So from ACF we would get, if we have an ACF where the spikes are only observed at certain lags, so then we say that it is a moving average process. If from PSCF we observe that there are spikes somewhere, now for ACF, if we do not observe any of the spikes, and for PSCF we observe spikes for 1-2 positions, then we can determine whether it's a autoregressive process of which order. Okay, so but if the ACF is like this, where all are like above and none of them is coming below, so then this is a clear cut signal of non-stationarity in the data set. So PSCF and especially PSCF we'll be able to get correctly if we have like stationary data. Okay, any question up until now?
No, ma'am.
Okay, so now as I was saying, we have that seasonally adjusted, or this one, the random component data. Okay, so let's say I'm working with this thing. So these are my random component time series, whatever I have obtained after removing the trend and seasonality components. Now if I have to get a ACF of this thing, I'm going to try and see. So this is not working because there seems to be missing values in this objects. So in order to remove this, we need another library called T series. Okay, and if I write this command na.action equal to na.pass, so you see here also at lags I see alternative things. So autocorrelations are a little alternating. So then also we cannot say that this is a pure moving average, because if it would have been a moving average of order 2 or 3, all other points would have fallen below this cutoff. Okay, we can also similarly get a PACF of this thing. So from PACF also we see that maybe at lag 1, 2, 3, 4 it is coming within the bounds, but then also it's crossing some areas. So it's not very clear whether what is the order of these, the whether this is actually stationary or not. Okay, so in order to test for stationarity, we can do some differencing and then we can check. So if we do difference of this thing, and we can see this difference series, then see this looks like the all the other spikes, even though they are crossing, they are not too far away. So from ACF there is no order, but if we do from PSCF, if we see, from PSCF also it's not very clear as to what we can say about this. So in order to test for the stationarity, we can perform the augmented Dickey-Fuller test. So if we can find here packages, if I can find adf.test. Okay, you can just Google only augmented Dickey-Fuller. This will test for unit roots. adf.test is in which package? Let me see. adf.test, if we try to run here, oh, it's in the T series package. So let me run this one. So somehow we have to tackle the NAs. Let me see how we can do it. So if we just remove the NA values, so this is present in T series package, right? So we'll go to T series and then we are going to check adf.test. Here we don't have anything, so some sort of manipulation will be needed in order to remove the NA variants and get the Dickey-Fuller test or something. Okay. So if the Dickey-Fuller test is significant, then it is going to show whether there exists any unit root or not. If rho equal to 0, then it will test whether there is presence of unit root or not. If the null hypothesis is rejected, then we would say that no, there is no presence of unit root, which means that it is If it has unit root, it will not be it will not be stationary. Okay, so if I can go to that tutorial or anything else, see here, this is how we should use. So the alternate hypothesis is stationary. If we can reject based on this p value, if p value is less than 0.05, then we would say that yes, the series is stationary. Otherwise, rho equal to 0 means that this series is non-stationary. Is it okay? Any questions?
No, ma'am.
Alright, so if not anything else, one more thing I want to show you, that is in order to get the critical points, how we can go about. So I showed you for F test. So if we need, let's say I want to get the critical point alpha percent for this distribution. Okay, so then I have to write QF 0.05. I have to specify the DFs, DF1 equal to 4, DF2 equal to 5, and this one lower dot tail equal to false. Now suppose I want to find a, let's say I have a why is this not working? Okay, so let's say I have a t distribution, okay, and I want the t 0.025 with degrees of freedom 18. So then also I have to do a same thing but with qt. I have to write 0.025 df equal to 18, and I have to get lower dot tail equals to false. If I want to do a left-sided test, I want to find out this one. The same thing I can find out and put a minus. Okay, so this would be qt 0.025 df equal to 18, and if I don't put this, you see, this, since it is symmetric, we'll have this just a minus sign before this thing. So we can use either of these logics to get the critical points. So all I'm asking is, in order to get the critical points, we have to use the qt, qf, q chi-square commands. So if I have something like chi-square 1, and I want the upper, this one, this, let's say this is my critical point. So the same thing I have to do, I have to write a q chi-square, okay, 0.025, that's the limit, lower dot tail equal to false, and df equal to 1. So then I get the values. Is it okay how you can find out the critical values using the software? So if you are confused about using the tables and how to use them, you can refer to the software and get the values. Okay. And also
Okay.
we should know about some plots, basic plots. Like for outlier detection, we should always get a box plot. In order to plot a continuous variable, we should always get a histogram. So I've shown you like plotting of linear regressions, the f tests. So tomorrow maybe I'll show you something else with respect to uh, logistic regression maybe. Okay, and how to interpret the coefficients, outlier detection, some part I'll try to cover that tomorrow. How to get standardized and studentized residuals, outlier detection, box plot, those kind of things I'll show tomorrow. Is it okay? Any doubt, any questions that you might have?
Ma'am,
Yes. Yes, ma'am.
No one.
Okay.
can you show me a Z test also?
Yes, of course. Anything
Means
else you
critical value.
want? Z test. I'll keep a log. Okay, so you tell me what you want. Tomorrow I'm going to show you.
No, critical value.
Okay, critical value for Z test.
Yes, yes.
That would be QT norm. Q norm, sorry.
Okay.
0.02501. Okay. Mean equal to 0. SD equal to 1. This is mandatory. You would get this as minus 1.96. And if you give lower dot tail equal to false, then you would get 1.96. Okay, same thing if you give 0.5 0.05, you would get 1.64. So these are the numbers that we readily refer to, that you can get through using Q norm. Okay, anything else?
Ma'am,
Hmm?
I didn't put some solutions.
Hmm?
Can you please send
Which solutions?
week 7, 9, 10, and 12 also?
I have already discussed all the solutions in the classes. So
Okay.
there are YouTube videos available. You can go here. You will find the problem solving session. Okay.
Yes, ma'am. It
So
is there. Okay.
yeah, here you will find a spreadsheet with all the links and everything uploaded. This is me. Okay, so
Yes,
for
yes.
each of the weeks I have solved there. So you can refer to the videos or the Excel sheets, or sorry, PPTs, and you'll find the solutions over there.
Okay.
Okay, anything else?
Tomorrow 3 to 5. Huh?
Yes, tomorrow 3 to 5.
Thank you.
Okay, so if not anything, I'll see you tomorrow. Thank you for joining. Thank you.
Thank you.